Number 22. Says the base of a triangle is shrinking. Base of triangle shrinking at a rate of 1 centimeter per minute. And the height is increasing. I'll try to condense this just a little bit, condense the wording. While height is increasing at a rate of 5 centimeters per minute. Find the rate at which the area is changing. Area is changing. Right, when height is 22 and base is 10. (22 centimeters) and the base is 10 centimeters. All right. So the rate at which area is changing. So the problem says to find, in notation, d area, d time, right when what? Height is 22, right when h equals 22, and they're saying right at that moment b is 10, the base is 10. I kind of already assumed h and b for the description of the height and the base. It seems natural. I didn't define h and b. I'm just going to write them here. This is fine for right now. All right, so if I'm going to find dA dt, I need to have some sort of representation for area of this triangle. All right, so we know the formula for a triangle's area is area equals 1/2 base times height. Right? I don't know if we really need a picture for this one per se. The formula kind of comes right out. We have bases and heights talked about and have an area. It seems like this is the natural relationship for this problem. Now, what do we know? It says the base is shrinking at a rate of 1 centimeter per minute. So that should mean, what do we know? We know that the rate of change of the base with respect to time is negative. This is extremely important. Negative 1 centimeter per minute. All right? So it was shrinking, so that means the derivative is negative. As opposed to the height, it said that the height's derivative, in so many words, was increasing, so a rate of 5. So we have 5 for dH dt and negative 1 for dB dt. So this pretty much nails down the idea that this is the correct relationship to start with, because once I take the derivative to find dA dt, on the right-hand side, since both b and h are functions of time, right? Even though they're just written as little variables here, they're really functions of time, because we see they're changing, right? The base changes and the height changes as time proceeds. So therefore, these are really functions of time. When I take the derivative on this side, these two derivatives will emerge, and I will have their values to plug in momentarily. So this is a really good start. So let's go ahead and take the derivative and get dA dt on the left. So dA dt, again, we have a little bit of implicit differentiation here. dA dt on the left equals, the derivative will bypass the 1/2 and apply itself to the b times h part. So that will be first times the derivative of the second plus the second times the derivative of the first. All right. There we go. All right. B times dH dt plus h times dB dt. Now we just need to figure what this is when h is 22 and b is 10. That should be no problem. We really have everything. They told us h is 22 b is 10, and the two derivatives we have from the beginning as -1 and 5. So everything is just now a plug-in to find this derivative value. So dA dt, right when h equals 22 and b is 10, will be 1/2. b is 10, we just said. Let me make sure I get this right. b is 10, and dH dt is 5, plus h is 22, and dB dt is -1. Okay. So we have 50 minus 22 is 28, I guess. So 28 on 2 is 14. And what are the units? Well, again, the easiest thing is just look back at your derivative. You have A units on T units, right? A is area. We were measuring in centimeters, so it should be centimeters squared. And time was measured only in minutes, so therefore it should be centimeters squared per minute.